Hello and welcome to today's webinar entitled 2014 IEEE Standards 519 Changes and the Impact on Your Power System Design Considerations. My name is Martin Pietschak. It's my pleasure to be your moderator today. We have an amazing turnout today with over 125 registrants from over 20 countries, spreading from North America to as far as Australia and New Zealand. Thank you very much for attending. We really would like to hear from you, so please ask questions and share your comments. Use the question and answer panel or the chat panel on the right side of your GoToWebinar player to share at any time during the presentation. We will attempt to answer as many questions as possible at the end of the session. Also, feel free to submit any questions after the event via email at Mirus International or join the conversation on the Mirus LinkedIn page. At this point, I would like to introduce our speaker, Al Archambault, Director of Sales at Mirus International. Al has over 45 years of VSD application experience. He's a graduate of Ryerson University in Toronto in electrical technology and worked with Canada Wire and Cable, Knockner Muller, Canron, Relcon Drive, Siemens, Teco Westhouse, and Mirus International. Al has been happily married to Fran for 48 years. Fran and Al have 5 children and 9 grandchildren. Today, please join Al in this webinar that will cover some of the recent changes made to IEEE 519. The webinar will focus on the guideline differences associated with low voltage systems. Al will use the installation of low voltage adjustable speed drives to demonstrate to owners, operators, and consulting engineers how the differences between the 1992 guideline versus the 2014 version may affect the designs when specifying and installing low voltage ASDs. Al, welcome, and over to you.
Thank you, Martin, and welcome to the webinar today to all our attendants. This presentation is not an extensive analysis of the differences between IEEE 519 and 2014 versions. It does, however, attempt to provide a practical working insight on the differences for design engineers as they specify, install, and apply low voltage adjustable frequency drives into electrical systems. We must remember that IEEE 519 is not an enforceable code. IEEE 519 is a guideline to be used by engineers for power system design considerations. Designers must use their experience and the guidance of IEEE 519 and a little common sense when writing specification involving the installation of adjustable frequency drives today. Before we go on, I'm just going to do a quick review on what are harmonics. This is a topology drawing of a typical PWM variable frequency drive. They're all the same today. They have 3 main parts: a diode bridge, a DC bus, and an inverter section or switching section. When you first switch on a variable frequency drive, the first thing that happens is the DC bus must be charged up. And the reason for that is they also have discharge resistors on them, so when you turn them off, the DC bus is discharged rapidly for safety reasons. Once the bus is charged up, then the inverter is ready to go. So what happens here is we have, let's say, a 480 volt, 3-phase, 60 hertz system, and the voltage is converted to DC and stored here on the capacitors. So a 480 volt system would produce a 640 volt DC voltage on the cap bank. Now, if you notice, I replaced the transistors with knife switches. That's the function of the transistors. They're insulated gate bipolar transistors. Today, there's new devices coming up, but the function is simple. They're fast knife switches, and if I was able to give you the sequence and the pattern required to switch the switches, and you were capable of switching at 2 kilohertz or 4 kilohertz, you could actually synthesize an output line-to-line voltage that looks like this. Now, the function of the switches is to control 2 things. They must control the voltage output to the motor and also the frequency. So the voltage is controlled by adjusting the parameter or the pattern of the switching pulses. The switching pulses actually create a sine wave current that goes into the motor. The motor wants to see a nice clean sine wave. Now, riding on this sine wave current is a sawtooth, and the frequency of the sawtooth is the carrier frequency of the VFD, the 2 kilohertz or the 4 kilohertz. The other thing that the switches do is they control the frequency out to the motor, and they do that by controlling the rate at which you produce positive and negative half cycles. Here's the speed formula for a standard squirrel cage induction motor. So the speed is equal to 120 times the frequency of the voltage applied divided by the number of poles wound on the stator of the motor. So a typical 4-pole machine on a 60 hertz system, its potential maximum speed is 1800 RPM, 120 times 60 divided by 4. Now, let's assume that we have a single-phase power supply and that the DC bus has already been charged up. Now, if I press the start button on this inverter, the motor is going to start turning and doing work and putting power out the shaft. Without the diodes connected here, this DC bus voltage is going to decrease rapidly because this is where the energy is stored to get the power out of the motor. Now, if we just think in terms of single phase, so I have 1/2 cycle here of a single phase power supply. And I like to simplify things when we start talking about voltages and what's going on with the DC bus. It's really simple. This represents time in degrees, and here's the voltage. An AC voltage is always changing. That's what these little blue dots represent, instances in time and as the voltage changes. So if I press the start button and the shaft starts turning, this voltage is going to decrease quickly. So it's already dropped to, say, 600 volts. So now I've got this sine wave voltage coming in. Let's assume we've got diodes here. When in time is the instantaneous value of this half sine wave going to be equal to or above 600 volts? Well, it's not here. It's obviously going to be up near the peak. And 1/2 cycle on 60 hertz is approximately 8 milliseconds. So the only time I have high enough voltage to overcome the DC bus voltage is going to be up in this peak. The only time that the peak voltage is going to be high enough is for 2 milliseconds at this region here. Okay? So just like the battery in your car, you can't charge the battery unless your battery charger has a voltage that's above the battery voltage. So the same thing is going on in this shot, where you see the result is a high amplitude pulse of current that goes into the cap bank. And this high amplitude pulse of current is discontinuous, and it's full of harmonics. And pulsing current does strange things to our electrical system. First of all, pulsing current increases eddy current losses in the steel structure of generators and also transformers. So eddy current losses are increased in these delivery devices. The pulsing current also increases I²R losses in conductors and windings of the generators and the transformers. So pulsing currents are very wasteful, and this is why IEEE 519 was introduced to prevent these wasteful pulsing currents from overloading the system or using up system's kVA capacity, plus the extra losses. The other thing that pulsing currents do that's negative is that they have to travel through impedances in the electrical system. So you have a transformer in your building. This is a picture of a switch mode power supply. Sorry about that. Switch mode power. And you can see the pulsing current here. And here's the voltage right at the pulsing device. So what's happened to this voltage is Ohm's law says that if we pass current through impedances, we're going to lose some of the voltage. So the result is the worst place for voltage distortion is at the device creating the pulsing current. and you can see that here. Now, remember, the pulsing current distorts the voltage. So if your building has thousands of these little power supplies in it, you can distort the voltage in the whole building. That's the other negative thing that pulsing currents do. So pulsing currents increase eddy current losses and I2R losses in your electrical delivery system, and they distort your system voltage. Here's an across-the-line full voltage starter for a motor. And a typical motor, if we started across the line, has a speed-torque curve that looks like this. Here's the load torque. So when we first switch this motor on, it's given 480 volts at 60 hertz. Remember, it's running across the line. It's not on an inverter. And it has a high starting torque capability, 120 to 150%. And it ramps up and goes up to almost 200%. And then the torque capability falls off until you pick up the load here, and you actually run at this little bit lower speed than synchronous. Now, if I don't give the motor the proper voltage, I affect the torque characteristics of the motor, or its speed torque capability, because torque is directly proportional to the voltage applied squared. So if I only had 336 volts because of voltage distortion, the torque capability curve of the motor changes to something like this. So you have lower starting torque, and you end up running at some higher slip. So there's more losses in the motor if you're not giving the motor proper voltage. So the key here is that the inverter must control voltage and frequency at the same rate that you change the frequency. So if a motor was running on a variable frequency drive at 60 hertz, we deliver 480 volts to the motor. If we adjust the speed to 30 hertz, we must drop the voltage to 240 volts. That volts per hertz ratio is very important. Now here's the current waveform of a standard 6-pulse drive. You can see it's even worse than 1 pulse. We've got 2 pulses per half cycle, positive and negative, and this waveform is very discontinuous, and it's 75% distorted. And this is going to distort voltage as well and cause extra losses in the generators, transformers, and I2R losses in conductors. This is an animation to show you why the current looks the way it does. This is line to neutral voltage and line to line voltage. Now the diodes commutate when the voltage between phases is maximum. So the first pulses that are created is when the voltage between A and B is maximum. We come out on A and return on B. The next pulse would be when A to C is maximum, out on A, return on C. The next pulses are created when the voltage between A and C is maximum, and again between B and A, C and A, and finally C and B. And that's why we call it 6-pulse, and here's your DC bus voltage, and that's why the current looks the way it does. So here's the current signature waveform we just saw animated. So using Fourier math, we can break this current waveform down. It's complex. We can't do math on a complex waveform very easily. So using Fourier's math, we break it down into simple sine wave frequencies, the fundamentals, 60 hertz, and then integers of the fundamental. And here's the formula we use for figuring out what are the harmonics, or the sine wave frequencies, that make up this current signature waveform we saw animated. So this is the N energy. This changes from 1, 2, 3, 4, etc. And P represents the number of pulses of our power supply. So the harmonics that are made up in this waveform are equal to the digit 1 first. 1 times 6 for pulses is 6, minus 1. The first significant sine wave or harmonic frequency in the waveform is the 5th harmonic, and that's 5 times the fundamental, or 60, or 300 hertz. The amplitude of that harmonic frequency is approximately equal to the fundamental current divided by the harmonic number. The next harmonic is 1 times 6 is 6, plus 1, The next one is the 7th, or the 420th hertz, and its amplitude. If I put the digit 2 in there, I got 2 times 6 is 12, minus 1. The next one is the 11th. 2 times 6 is 12, plus 1. The next one is the 13th. So here's the current signature waveform. So we've learned now that harmonics are sine wave frequencies that make up this current waveform. So the first harmonic is the first, or the fundamental, that does the work. The next one is the 5th, 300 hertz. And I'll just put the 7th in here, the 7th. And what we did here is we actually took the instantaneous values of this 7th sine wave frequency and the 5th sine wave frequency and the fundamental, and we just added them up arithmetically. And son of a gun, look, we traced out the current signature waveform. And now everybody knows what harmonics are in a nutshell. Here is NEMA MG1 Part 30 derating curve on motors. And what I did here is I used the derating curve for a system that had 5% voltage distortion on it and 8% voltage distortion. So right out of the NEMA guidelines for motors, it shows that with 5% voltage distortion caused by these pulsing currents on your system, you should derate a motor to about 96% of its nameplate horsepower rating, assuming you're trying to deliver full power out of the motor. Now, most motors have a service factor, so you would be eating into the service factor and still be able to deliver rated power without overheating the motor too much. Now, you can see if the voltage distortion is 8%, you have to derate down to about 89% of the motor's capability. So right away you can see that background voltage distortion caused by harmonic current pulses can degrade your electrical motors and cause them to overheat and fail sooner. Here's a typical submersible pump. This one was operating in New Zealand. It's a submersible pump, so it was water cooled, by the way. And this submersible pump was subjected to background voltage distortion in the area of 12%. And the extra slip losses caused in this motor by the high frequency distortions actually created so much rotor losses, it melted the bars out of the motor. This is reality. So high current distortion causes problems. It increases eddy current losses in transformers and generators, increases I²R losses in conductors for transformers, windings, and generators. It causes high background system voltage distortion that can do damage to all kinds of things. High background system voltage distortion causes problems. Failures of switch mode power supplies in PLCs, computers, and instrumentation. Generator automatic voltage regulator malfunctions. It can cause false readings on critical sensors and instrumentation on industrial lines. Increases operating temperature of AC induction motors, windings, and also on the rotor bars. So now we're going to get into the differences between IEEE 519-2014 and 1992. The first item is the limit for current total demand distortion, TDD. There's no change there. Next important item is that for the limits for total harmonic voltage distortion, they've added a new voltage range. They split up the old voltage range, which was 120 to 69 kV, and made two. One is 1,000 volts and down, and then the balance 1,001 to 69 kV. And they used to have a special load for hospital, airport, and dedicated loads, voltage distortion rating, and that's been eliminated. And then the point of common coupling definition has changed. So the first item, we look at the limits for current distortion. There's no real change there. Here's the item from 1992. You can see the TDD levels are the same for the given I short circuit diode ratios. So now we're going to look at the voltage spec differences. They've lightened up on the voltage background voltage distortion requirements. The first thing they've done is they added this new range. The old range was 120 volts to 690 kV, and the voltage distortion for that range was 5%. In the new guideline, they've split it up. So they've got below 1,000 volts. They now have the maximum allowable is 8%. Remember, it used to be 5. That's what this said over here. Now it's 8%. And for individual harmonics, they can't be higher than 5%. The balance of the voltage range is the same as the old. So it's still 5% at medium voltage, and the maximum individual can be 3%. The next item was the special voltages distortions for hospitals and dedicated systems has been eliminated. So you can see here it's no longer there. Okay. And point of common coupling. Now I'm going to read these definitions. You see the significant difference. So here's the 1992 guideline. It said that the point of common coupling is a point of metering or any point as long as both the utility and the consumer can either access the point for direct measurement of the harmonics indices meaningful to both, or can estimate the harmonic indices at point of interference. And it further went on, within an industrial plant, the PCC is between the nonlinear load and the other loads. Now, this left it open for interpretation. Basically, the point of common coupling could be anywhere that someone decided it should be. The new definition, they've restricted it and pointed directly to where IEEE 519 wants the point of common coupling to be picked. So in the new definition, it's a point on a public power supply system electrically nearest to a particular load at which other loads are or could be connected. The PCC is a point located upstream of the considered installation. The recommended practice should be applied at interference points between system owners or operators and users in the power system. The PCC is usually taken to be a point between the system owner and a system user where the system owner or operator can offer service to another user. Frequently, for large industrial plants, this point is at the medium voltage side of the distribution transformer. For commercial users, office parks, shopping malls, etc., the point of common coupling is on the low voltage secondary side of the service transformer. The recommended limits should be applied at the PCC and should not be applied to either individual pieces of equipment or at the location within a user's facility. There's a significant difference there. Now, what does that mean? Let's look at what it means. Here's a hospital. Here's a utility transformer. Here's the transformer that the hospital owns. And the secondary voltage of the hospital transformer is 480 volts. This hospital has some fixed speed fans. It has 3 chillers. It's got an emergency department. It's got X-ray equipment. It has operating rooms, and it also has intensive care. It's not a big hospital. There's a lot of nonlinear loads in a hospital. Chillers have variable speed drives on them, etc. X-ray equipment has power supplies on it, and hospitals are filled today with all kinds of switch mode power supplies that are controlling critical equipment, monitoring babies and patients. So what happens here? This is a solve program that Mirus has, and I actually plugged in all this data and ran the simulation, and I've got some information out here that it told us what was going on. And at this point here, the 480 volt side of this transformer, it's saying that the voltage distortion with these types of loads is 11.5%. If we look at the new guideline says we need to be 8%. Remember, the old guideline said for hospitals it should be 3%. 3 to 8% is a significant difference, especially for hospitals. So you have to use some common sense when you start to apply IEEE 519 to places like hospitals. The primary side, or the secondary side of the utility transformer, medium voltage side, the voltage distortion is 4.7. It meets IEEE 519 guidelines for voltage distortion. Yet, on the 480 volt side of this hospital, we're way above the 8% and way above the old 3%. Keep this in mind when you're applying IEEE 519 to your systems. Okay, let's do a review. The current distortion limits have not changed. Remember, it's the current distortion that affects the level of voltage distortion at various points in the electrical system. The voltage distortion limits were relaxed for systems rated below 1,000 volts. Individual harmonics must be kept to 5% instead of 3, and 8% instead of 5. Also, special application limits for hospitals and airports have been eliminated, meaning IEEE 519 acceptable limits for voltage distortion in hospitals and airports is now 8% instead of 5. The PCC is usually taken to be a point between the system owner and the system user, where the system owner or operator could offer services to another user. Frequency for large industrial plants, this point is at the medium voltage side of the distribution transformer. For commercial users such as office parks, shopping malls, the PCC is at the low voltage side, secondary side of the transformer. The recommended limits should be applied to the PCC and should not be applied to either individual pieces of equipment or at the locations within a user's facility. Remember, IEEE 519 is not an enforceable code. IEEE 519 is a guideline to be used by electrical engineers for power system design considerations. It is still up to the individual design engineer to use his experience and a little bit of common sense and the guidelines when writing specifications for a given power system. Thank you very much.
Thank you all. Let's open up the panel and allow Al to answer some of your questions. If you haven't done so already, we invite you to submit your questions via the question and or the chat answer panel on the right of your screen.
They'll call me before it goes, and then you both get their own impact. Yeah, don't worry, I don't get it.
All right, so we have a few questions coming in. So for the PCC, and the PCC is now to be taken as a secondary side of the main utility transformer, correct? No?
Well, again, you have to use common sense, but the guideline is definitely stating that the PCC is the secondary side of the utility transformer. if it is in a shopping mall or office mall. If it's an industrial complex, the PCC should be the medium voltage side of the utility transformer. That's what it states.
Another question. Do you have a sample specification how to make sure 6 pulse and 12 pulse drives meet this new standard? From Mark.
Yes, we can supply a specification that talks about that.
Some people are asking if we can send the presentation to after the fact, and yet the answer is yes. Everybody will receive an email with the links to those presentations for later viewing. So one of the questions is, will there be a new version of Solve taking the new guidelines into consideration?
Yes, we're going to revise the Solve program to take the new guidelines into consideration.
Is there any more questions? We recommend you send them now. Otherwise, we'll be wrapping up very soon. Okay, it looks like we don't have any more questions. I do invite you, however, to submit more questions our way, either by contacting us at mirusinternational.com or contacting Al directly at al@mirusinternational.com or calling him. We also invite you to download the free software, the Solve software you saw earlier, at the www.mirusinternational.com. This is all the time we have for our webinar today. Please look for our follow-up email that will alert you to the on-demand status of today's event so that you can review any material you missed or simply go over it again. On behalf of Al and the Mirus team, thank you for joining us today and taking the time to view our presentation. Have a great day, evening, or night.